Hello, I am Shubham Papade, and in this video I will be talking about distance vector routing protocol and the implementation of this protocol using Python programming. So this assignment talks about implementing the distance vector routing and in which we use the Bellman-Ford equations. So the input format is given as the number of routers, then the name of routers, and uh, the distances, or we can say the topology of the network, and then the end of file. And for the output, I have implemented the output a little bit different, but which is simplified version, so we will be able to understand most of the stuff easily. And for each computation the router should wait for seconds. This protocol I implemented, I will be explaining further. So let's now dive into the explanation and the code. So here comes my first version. So I have implemented various versions, as you can say, but the three main root versions are dvr, which continues till infinity, and the converging dvr, and a dynamic changing dvr. So the dynamic changing dvr is the generalized version of the distance vector routing that I have implemented, so which is the best one, I can say. And others are just some same version but some different programming, like. So diving into the first program, so I have used threading library from Python, queue method, and some time variables to get time analysis. So first I have developed the router class, which represents a whole working router. So I have I have defined the initialization of the router, then adding link between the routers, and displaying a router table, sending router table to other routers, receiving routing tables from other routers, and updating the router table. So these are the core functionalities of the router class. And then I have defined a function which is parse input. So that particular function is for parsing the input in the given input format. So then I have this main function which takes file path as input, and which is a txt file. Then we do the initialization of different routers from the input, like if the input is like say this input abc3, abc, ab5, ac2, and end of file, then there will be three routers which are named as abc, and the topology between them is ab5 and ac2, like ab are at distance 5, AC are at distance 2, or we can say the time taken for the packets for this distance to cover is 5, like the topology. And then we have initialized those bidirectional links. We have considered a graph like structure between them, so the router topology. And then what we have done is started threads for each router. So this code here starts thread for each router, and then we wait for each thread to finish here. And for updating the routing tables, I have kept iterative version. So here I have initialized the iteration to be 1, then I have written one try except block, wherein till infinite we do iterations which checks whether router is updated, is there any different route for packets to go. So for that, here I have started new threads for sending routing tables, and we have again waited for all threads to finish, and then we have displayed the result of the tables for that particular iteration. So those iterations will keep on happening in this version of dvrContinue. It will keep happening till the infinity, and we will get the table copy each 2 seconds. So we will first run this code on a sample input 1 file, which is already given in this assignment page. So running on this, so here you can see iterations are happening. Here you can see no outer update is done now. For the first scenario, the router got updated. Here updated table, updated routers here B and C routers got updated, but later on, as you can see, the table got saturated, like it has converged, and then there is no router update. Here we can see that the assignment is pretty much restricted to the initialized condition of router and their topology. That's why I have written another version where we consider dynamic changes, like the program is continuing, and in between there are some link value changes in the router topology. So the first version is currently running. We will stop it, and now here you can see current routing tables after 35 iterations, like in A router, destination A has cost 0, destination B has cost 5, destination C has cost 2. So in cost with itself is 0, and for B, C we will check the graph. Like here is the graph for the first topology, A, B and C. The weight between cost between A and B is 5, A and C is 2. So here we can see for the current version, A to A is 0, A to B is 5, A to B is 5, A to C is 2. Here you can see A to C is 2. And for other routers as well, we must check A to C, like B to C. Here you can see in B's router, distance to C is 7. Here you can see B to C is 2 plus 5, that is 7. So we can say that the algorithm is pretty much working correctly. We will run for another case, like input 2. Here you can see the input 2, and I have formed a graph here for that input, which is having 4 nodes like routers and their topology. Here you can see the topology as well. We will run the program. Here you can see iteration 0, iteration 2, iteration 3. Now there are no router updates, but initially there were router updates. Updated table CBA. So yeah, as you can see here in this version, like after 11 iterations, the current routing tables are like this, and these are converged routing tables, but we have not stopped the algorithm yet. In this version I have converged the algorithm. So here router table of A says A to A cost is 0, which is correct. A to B is 2. Here we can check A to B is 2, minimum cost is 2. The minimum cost for A to B is 2. Then A to D is 1, A to D is 1, then A to C is 5, A to C. A to C minimum cost will be 1 plus 11 is 12, 1 plus 7 plus 3 is 11, 2 plus 3 is 5. So this will be the minimum cost. So 5 will be the minimum cost. It says A to C is 5, which is correct. Indeed. For other like router table C, we can see C to D is 6. So C to D, here direct link is 11, but C to B to D is 3 plus 7 10, but C to B to A to D is 3 plus 2 plus 1, which is 6, so that will be minimum. So our algorithm is indeed correct. So yeah, these versions are working fine. Now you can see the converging version, like we will run for the input 3, which is a complex mixed version. So I will run for that. So here you can see the algorithm is going on. Now this algorithm converges, and here you can see the final routing tables. So routing table of A, B, C and so on. So for let's say a random routing table for E to E is 0, E to B is 7. In this graph, this is the topology. So here we saw that E to B is 7. E to B is 7. Here you can see the distance cost. So this is 8, this is 9, so this is the minimum cost, which is correct. E to A is 7. E to A is 7. This cost is the minimum. Let's say we want to see A to F in the routing table of A to F, which is 8. Let's say A to F 2 plus 7 plus 1. That I think this is the minimum one. This is 9 and this is also 8. So yeah, this one is the minimum. 5 plus 2 plus 1. So A to F is 8. So in the routing table of A to F is 8. The routing table of F to A is 8. Here we have considered them to be bidirectional, as those topology will be bidirectional indeed in the real world. So we can see the algorithm is working pretty much fine. And in this algorithm, here you can see that first I have given the for the iteration 0, I have given the router edges and their costs. So destination in the router of A, destination A, cost is 0 and so on. Then I have implemented these calls by which we will be able to see how the routers and their threads working exactly. So here you can see table B is sent to A. So router B sends its own table to A. So router A is sending its own table to B. Router D is sending its own table to A, and so on. So here we can see how the sending of table happens. Then in the next iteration, those routers receive those tables. So A receives B, A receives D. Then the updation of BD happens in the A router, in those B and D particular routers. Then B receives A, B receives E, B receives C. Then updation of AEC. How those particular operations happen, that I have implemented here, so we can see what all things happen. So that's pretty much great. If you don't want to see them, like it's pretty much clumsy and cluttery. So if you want to remove those, you can remove those here in the send, receive and update. So that will be pretty small output for you. So here is the output, initial costs. Then in this iteration 1, A, B, C, D, E, F, all routers got updated. In the second iteration, A, C, D got updated. Here we see the convergence and there are no more updates. So here is the final routing table. So I programmed them really well, so that's good for me. And now let's move on to the best version that I have implemented, which covers many things other than those mentioned in this file. Okay, this file contains all the stuff till this. So here what I did is you can see if you refer to the computer networking top-down approach featuring the internet book by Kuros. you can see there they have referred to as if there are changes in those links, like the costs. Let's say the topology is like x to y, x y z, x to y is 4, y to z is 1, x to z is 50. This is the example from that Kuro's book. So let's say what happens is there is a change at some time, 10 seconds. I have considered 10 seconds, which is the seconds after our program starts. So there is a change between link xy. Here xy was 4. Let's say there is a change from x to y, which becomes the link cost becomes 1. So now our Bellman-Ford algorithm should again work and get the optimal cost, right? So for that I have implemented this dynamic changes dvr, which works even when there are changes in between. So for this other things remain same, but I implemented another parsing change file and some different kind of updating router table, a little different, and this monitor changes function. This monitor changes function is dedicated to this. So if there are any changes, we see if the current time minus the start time of the program is greater than or equal to the timestamp mentioned in the change file, this 10. So what we are doing here is we are simulating the router mechanism which happens in the real practical world. So if this condition is true, like for just this iteration the change happens, then we are doing what? Router's source, we are adding the link to that destination with that new cost, and for destination to source we are adding that new cost because the link is bidirectional, right? So now what happens is again the Bellman-Ford equation gets used for updating the router tables. And how I have implemented that is I have implemented another background thread. Here you can see, which monitors those changes. Our program is just like previous program, but I have considered a background thread which I have considered as a daemon, so it doesn't block the current program termination, so that our program will be able to gracefully exit. So the thread is using monitor changes function, and the arguments are router changes and start time of our program. So now here you can see our initial state was topology was x to y is 4, y to z is 1, x to z is 50. I will show you here. So our topology is x to y is 4, y to z is 1, x to z is 50. So now what we will do, we will run the program. With those particular files, input.txt and change.txt. Here you can see we have considered the change to happen at 10th second. So the program continues to go until this iteration, 13th iteration, the time lapse is 28 seconds. So the change has been happened. So for now there is no router update, so we will terminate the program. But see, initially the destination to other routers cost are these, then we are sending the tables, then for the first iteration time pass is 2 seconds. So till now 2 seconds have been passed. So for this second receiving the tables and updating the tables, the updated tables updated routers are x and z. So initial router information was high, so we have updated them. So now the current routing tables are x to x is 0, x to y is 4, x to z is 5, x to y is 4, x to z is not 50 but 4 plus 1, that is 5, y to x is 4, y to z is 1, y to x is 4, y to z is 1, and z to y is 1, z to x is 5, z to y is 1 and z to x is 5. So let's say for the 10 second we have considered a change happened, that is the link change from cos 4 to 1 at 10 second. So here you can see a change got detected. Till now the router was converged, but a change got detected at timestamp 10 that the link x to y has got the cos to be 1. So now our router table should change, right? So now what happens is the router tables for x and z got updated. So here you can see the all implementation. So maybe we can remove those cluttery information to get only the needed part. So we will run the program again. So yeah, the program is running. Initial cost, time pass to updated router xz. Now no router is getting updated, no router is getting updated, but the change got detected. Now x and z got updated, right? A change got detected, then routers x and z got updated, and now as it changed from 4 to 1, right? This 4 got changed to 1. Now the cos will also change, right? So now x to y becomes 1, x to y becomes 1, x to z becomes 2, x to z becomes 2, and so on. Z to y becomes 1, z to x becomes 2, z to y becomes 1, and z to x becomes 2. So now here we can see it is updating. So change got detected fast. Okay, according to what Prashant sir told, the change got detected fast. In the course book also it is mentioned this, they have mentioned this. So again the iterations are currently happening, so now there is no change. We can also check for some another changes, like there can be multiple changes, like x to y changes to 4 3, then again x to y changes to 2, let's say. Now if we run the program, here we can say at what time this change happens. Let's say at 6 seconds, and this change happens at 10 seconds. So now running the program, we can see now currently first xz routers got updated, and then no router is getting updated. Now the change is detected for x to y becomes 3 at timestamp 6. So now again xz got updated. Now again the next change got detected, x to y becomes 2 at timestamp 10. Till then no routers was getting updated, but now x and z got updated, and now there is no change. So this is the converged state, so no router is getting updated. So we'll stop the program. But as you can see, there is a glitch, right? If this x to y link gets, let's say, a cost of 60, this example is also mentioned in the Kuro's book, which is high cost. So the book also mentions that here we see the routing loop problem, count to infinity problem. So this algorithm doesn't account for that problem. Okay, I have kept it that way to see what things goes wrong. So now running the program, initially the costs were good, exit order, now no router update, the distance are good, but now a change got detected, x to y becomes 60. Okay, these are the current routing tables. But what suddenly happens is that again y x to y is 6, x to z is 5. Let's see here, x to y becomes 60, right? Now here we can see x to y becomes 60 means y to z is 1 minimum distance, x to z is 50 and x to y is 51. So in router table of x, y should be 51 and in y's x should be 61, but here it says 6. So this is the count to infinity problem, and here we see a routing loop. So here what happens is already the routing table of z was containing y distance to y to be 1 and distance to x to be 5. So what z sends to others is that z sends others that I can reach x in 5 cost and y in 1 cost. So then x is that through z I can go to y with 5 plus 1 cost, and y sees through z I can go to x through 1 plus 5 cost, which is not the correct case, right? That is wrong. But that's what the bug in this algorithm is. We couldn't account for those count to infinity problems. The changes, if the cost decreases, then that change happens very suddenly. But if the cost increases very drastically, we get in the count to infinity problem. For that, there is a method called Poisson reverse. So in which we do the cost to other routers see the cost to the another router which is the neighbor of those changed routers to be infinity. So by that we will be able to make this algorithm better, which works and do not go through that count to infinity problem. So for this version I haven't implemented because my motto was to see how that happens, how the problem is. So maybe in upcoming days I will be able to do that and I will do the same. For now I think that's pretty much about it, and I dedicated my most of the time to understand the theory, understanding the DVR. So distance vector routing is a really good algorithm which was implemented in the past. So that's what I did in this assignment, and I enjoyed doing this assignment. I thought the assignment was really practical, and I will be doing the next upcoming version, like including the Poisson reverse method for getting rid of this count to infinity problem. So that's pretty much it, and I think you all will be loving this dynamic changed version. Thank you so much.